welcome everybody. For the next 40 minutes or so, we'll be talking about the big wave of AI at scale. We are going to see some examples of what AI at scale can do, including some of the products that you already know and what it means for you, all of you. So let me start first by showing you a vision of how we talk about AI at scale for the first time back in March 2020. So this is more than 2 years ago. And by the way, we have a lot of content, a lot of demos to show. Some people from our team are in the chat. So if you have any questions during the presentation, please just jump ahead, write your questions, and some people from Microsoft will be answering the questions. With that said, let's look at a video from a bit more than 2 years ago when we talk about AI at scale for the first time.
Our ability to communicate, to express ourselves through written, spoken, and visual language is a fundamental aspect of what makes us human. If we want to create an artificial intelligence capable of augmenting human ingenuity, we must start with language. Innovation hinges on our ability to see the world differently, breaking boundaries and looking in unexpected places to help solve some of the world's toughest challenges. As humans, we master language by making connections. It takes us many years to learn about the relationships between words and the importance of context. I'm a new father to a 1-year-old girl, and I see her learn little by little about language. Every night, we read her books with pictures of animals, things, and places, my wife in English and I in Spanish. Basically, we're giving her large amounts of language and image data in 2 languages, and I can see her starting to correlate concepts across the 2. The other day, she saw a pup in the street, and when my wife asked her what it was, she said, dog. And I asked her, she said, perro. There is hidden complexity in seeing an object and then identifying and accessing the word or words needed to describe it, and then doing this in multiple languages. Now, imagine what it might take to understand a sentence, a whole Wikipedia article, or an entire novel. In the past, we used rule-based systems to try to mimic this understanding in machines, but there was not genuine language comprehension at all. Later, we taught these machines how to model language in a mathematical way with vectors. Still, this didn't really give our machines a rich understanding of conceptual relationships. What was missing was context. Today, our language models are learning language by essentially reading the book through an approach called self-supervised learning. It works like this. We give our model a huge amount of text, and as it processes the text, we ask it to predict words based on the surrounding context. As the model does this hundreds of millions to billions of times, it starts to build an understanding of the underlying language concept and grammar. We think of the development of AI similar to how we think of the development of the human brain. Synapses between neurons build cognitive capabilities in humans, and in AI, these neural connections are called parameters. A year ago, the largest AI models had around 1 billion parameters. Our latest model, called Turing, has 17 billion. We anticipate that the trend will continue into the hundreds of billions of parameters and then trillions. The only way to train a model with billions or even trillions of parameters is with large-scale infrastructure composed of clusters of hundreds to thousands of machines with specialized hardware, all interconnected by high-bandwidth networks. The Azure cloud provides us with such clusters. We then need to distribute the training of the model across all of these machines. Over the past year, we have developed optimization techniques that reduce the resources that we need and still train models faster on the same infrastructure. We have recently open sourced these techniques to enable everyone to train large AI models much more efficiently. General language is sometimes not enough to support the tasks needed. Let's say you give a human a foundational education where they gain a general understanding of the world. This is similar to how we develop our AI models. We start with a high school level model, which has learned from all the data available on the internet. We send this baseline model to build on its abilities in specific domains. For example, the productivity domain for Office, the business domain for Dynamics, or the professional domain for LinkedIn. As our language model learns from domain data, it does so within the context of each organization in a privacy-compliant manner. An emerging generation of even larger models is now learning from this data and functioning in a more generalized way, combining language, images, video, and speech. Even with these amazing recent achievements, the reality is AI is still in its infancy. For example, we're still far from AI that can use common sense reasoning to draw conclusions. In the search for greater intelligence, civilizations and humanity thrive. Every time we reach a new AI frontier, we realize we can do better. As research advances and we magnify human intelligence with artificial intelligence, we may gain a clearer and deeper understanding of ourselves and of one another.
So that was from a bit more than 2 years ago, and the past 2 years have been very interesting, and you can see some of the articles from the press talking about a bunch of things coming out of Microsoft, like talking about that Turing NLG model, the largest model in the world back in 2020, and Microsoft building supercomputers for AI, and there is an example of a supercomputer again, like a bit more than 2 years ago with 10,000 GPUs. Microsoft and NVIDIA working on language model over more than 4,000 GPUs. Microsoft is starting a partnership with OpenAI to collaborate on large-scale AI. Some of the models coming out of our partner OpenAI, like GPT-3, that has learned to blog and argue and code, and AI writing computer code now, and now OpenAI's DALL-E becoming a very good graphic artist, etc. So it has been a lot of motion in what we have done, and all of this is fueled by research. First, we have 8 research centers around the world, 1,000 plus researchers, more than 20,000 patents on the AI space, 1,000 plus published papers, and achieving human parity on things like vision, speech, language, etc. Besides research, all of this AI innovation has been enabled by an explosion of data, an explosion of specialized compute. So on the left side, we have the digital universe of data in exabytes in the world. This is how much data we have at different points in time. And you can see in 2020, we hit 40,000 exabytes or 40 zettabytes. And you can see by 2025, we estimate 175 zettabytes. So a huge amount of data generated from web and cloud and the edge and IoT devices, etc. Similarly, on the compute side, you can see on the blue line the performance of single-threaded general-purpose computing on CPU, and you can see how it has started to slow down. Whereas on the other side, on the very specific context of machine learning and artificial intelligence and the type of operators that we have, including linear algebra, for example, these multi-core, multi-tensor specialized devices, particularly GPUs, are still substantially increasing year over year. And if you look at scaling up and scaling out of this compute across multiple GPUs in the same server, or multiple servers in the cluster, this acceleration is even more. So we estimate by 2025, the estimated acceleration of specialized computing is going to be around 1,000 times more than general purpose computing in the context of AI. So we're in this new trend of AI that we call AI at scale, and there are 3 aspects that are supporting this trend. One is self-supervised learning, and we'll talk a little bit about each of these. The other one is the transformer architecture, and finally, transfer learning. So in the case of self-supervised learning, AI models are learning contextual representations from the data itself. So currently, we can show these models large amounts of data, and we can mask specific words or specific sentences, and have the models predict these words or sentences. And we can do this over text. We can do this over images. So we can, for example, pause some specific mask some specific parts of the image and have the model trying to identify it. And these are very high-level parallelization operations. The transformer architecture allows you to encode and decode representations of the data. Right, so from particular sentences, you can identify this as well. And you can encode this into multidimensional embeddings in the space. So for example, here, you can identify there is a particular word in the sentence, something like the young boy always carries his teddy bear with him, and you can look at his and you can find that his is related to boy, his is related to teddy bear. And then you can represent all of these combinations and representations of embeddings in a multidimensional space like you have here, in this case, simplified into a three-dimensional space. Through transfer learning, while in the past we used to train models for a specific task like sentiment analysis or content moderation or face recognition, today we can train a model that learns these contextual representations of some space, like it can be text, for example, or it can be images, and then use this as a base or foundational model to support a large variety of tasks. You can support tens or hundreds of tasks. And what this allows you to do is that you don't need to train these models from scratch. You need to train one of these foundational models once and then use it in multiple places. And it also removes the need for labeling data. So you don't need to have a substantial human effort labeling data because the models are learning from the data itself, these representations. Now, we have, together with our partner OpenAI, learned that larger models are able to abstract a richer understanding of the underlying data. And you can see this through this scaling laws of AI, and this comes from a paper from OpenAI, where on the top side, you can see how the model capability increases with compute, data size, and model size. On the left, you have, as on the x-axis, you have the data set size. You can see the number of tokens increasing in the case of language. On the y-axis, you have the loss function. So basically, you want to reduce the loss function as the training continues. And you can see how, as the data augments, the loss reduces, and that's expected. You can see in the middle how, as the amount of compute that you have in the cluster increases and the amount of processing time that you spend on the model increases, similarly, the test loss decreases. And finally, you can see as the number of parameters of the model increases, as the size of the model increases, similarly, the loss function increases or the error decreases. Now, on the bottom side, what you can see is how the efficiency on the training of the model and the capability to learn from the model increases also with model size. So we have different models plotted with different colors. So smaller models are plotted with purple and blue, and bigger models are colored as yellow and green. And you can see on the left side how, as the number of tokens increases, so as more data is shown to the models, bigger models are able to lower the error in the function of the prediction even more. And you can see how, even with the same amount of data, bigger models are able to lower that error function even more. Then on the right side, what you have is the amount of compute in petaflop days. And what you can see is how the smaller models, like the purple models, they stop lowering the error function at some point. Even if you give them more compute, like they're not able or capable of furthering lowering the error function. Whereas large models can continue lowering that function over time, the more compute that they get. Because of this, we have continuously increased the size of models that we train, and you can see this chart showing the size of models in billions of parameters over time. You can see in 2020, we had the Turing NLG model, and that model was 17 billion parameters, and it was trained on 150 billion tokens of internet text. So just for comparison, all of Wikipedia is only 4 billion parameters. That model was trained on 512 GPUs. At that point, the fastest GPUs available were the B100s from NVIDIA. Then you can see GPT-3, 175 billion parameters trained on almost 500 billion tokens and trained on a top 5 supercomputer for a few months. When we look at Turing NLG-V2, the second version of the model that is in research currently, and the model is 530 billion parameters and has been trained on 300 billion tokens, trained over 5,200 of the latest GPUs, the A100 GPUs, and it has been trained for multiple months. So very roughly, if we think that the human brain has around 100 trillion biological synapses, and you assume, again, very roughly that one biological synapse corresponds to one model parameter, it's interesting to think if a 100 trillion parameter model will be able to do what the human brain does. So let's look at how these models have progressed over time. Let's look at this first Turing NLG model. Again, this is back in May 2020, and let's see what the model was able to do.
Let's start by asking the model some questions based on the large amounts of web data that it used for training. How many people live in the US? It's over 300 million people. That's correct. When did we first land on the moon? 1969. Accurate. Let's see how it does with things that I like. What DC Comics team were the Avengers modeled after? And that's the Justice League. And what are the Enterprise's main weapons in Star Trek? Phasers and photon torpedoes. Nice. Let's now copy and paste a document that the model has never seen before, like this memo from Satya about the Microsoft response to COVID-19. And let's ask the model some questions about it. How many messages does the healthcare bot respond to? You can find the answer here, 1 million messages per day. Great. What was the first for the University of Bologna? With some semantic understanding of the content, you can find the answer here. They moved 90% of its courses for 80,000 students online to Teams in 3 days, which is awesome. How are Power Apps and Power BI being used? They're being used to manage bed count and inventory of critical supplies and sharing that information with others across the region. Amazing. How are scientists using GitHub? To power a distributed computing project to assist researchers developing potential therapeutics using volunteer computers, which is fantastic. Before we move on, let's settle the Star Wars debate of who shot first in the Mos Eisley Cantina by copying the Wikipedia article about the scene and then asking the model the question, who shot first? And there you go, Han Solo. Now, let's ask the model to summarize a piece of text, the story of Romeo and Juliet from Wikipedia. As the model reads the text, it abstracts the most important ideas from it and stitches them together in a cohesive summary, tweaking it as it makes progress. Look at the completed summary. I really like how it goes to the point. Let's now summarize a complete long article about Microsoft's commitment to be carbon negative by 2030. Once again, as the model makes progress on the article, it abstracts the most important ideas into the summary, reassessing the relevant priority and tweaking the summary accordingly while maintaining cohesiveness. Given the length of the article and the importance of multiple aspects, this is going to be a much richer summary.
So what we saw in the previous demo was that Turing NLG model that we showed, again, more than 2 years ago, synthesizing answers from documents that he had never seen, summarizing articles and documents that he had never seen before. So let's look at other examples of other models. So here we have GPT-3 from OpenAI, a model that is able to articulate human-like text. So in this case, the example is a human asking GPT-3 how to build a board of directors for a startup. So GPT-3 is synthesizing all of the very, very large amounts of data that it has learned from, and then writing a whole new article that did not exist before. So it is not just putting together copy and pasted articles or pieces from the web, but actually word after word and sentence after sentence, generating a whole new article. So here you can see it has a bunch of recommendations. I spend time with the founders and try to identify some potential enterprise customers that may want to participate in the board. here's a target list of potential 20 to 25 people that you may want to look at, like current investors, your own portfolio companies, current and former colleagues, etc. And blah, blah, blah. It keeps walking you through 3 steps on how to build your board of directors for your startup. There's another example where we have an Argentinian computer scientist, Manuel Harauz, and he's having a chat with Albert Einstein. In this case, GPT-3, thanks to its understanding of Albert Einstein based on either documents that Albert Einstein wrote or information on the web talking about Albert Einstein, is able to articulate how Albert Einstein will respond to things and what is the type of facts that Albert Einstein will base a conversation about. And you can see different back and forth between Manuel Harauz in 2021 and Albert Einstein. So interesting how is the model is able to abstract even the type of communication of particular people as well. So interesting to think, will writing, as we know it as human, is going to change in the next few years as authoring tools become better at articulating the desired content that humans want to see in a document or an article. So this is Turing NLG v2 under research, and we can see as the models increase, it's starting to show new emergent behaviors that we hadn't seen before. And in this case, what we have seen Turing NLG v2 being able to do is solve riddles. So in this case, you may want to try to answer this one. It's a riddle that did not exist on the internet. I'm pretty sure it doesn't exist yet. Somebody in the team just came with it, and it says, all of us have one, but few get to choose. If you don't know mine, you don't know my friend. When it is called, our attention is drawn, and even if we're gone, they're still around. So let's see if the model can figure it out. So the model says, well, I think the answer is a name, and then it starts describing why it thinks the answer is a name. So you can see how the models are developing this even richer understanding of language to be able to do things like solving riddles, for example. So we're rapidly adopting these language models in our products, using them in things like Bing, for example, for better search and question answering, Word for better reading and better writing assistance, Outlook for better email management and preparation of meetings. In the case of Teams and SharePoint for better knowledge management. In the case of Dynamics for better customer engagement, LinkedIn for better matching of jobs to candidates and vice versa, and better content moderation. And same thing in Xbox Live, particularly as we work very hard on detecting and moderating bullying. And we are using these large models in all of these products simply because they work better than anything else that we have done before. So any just either traditional software-based approaches, heuristics, classical ML, or even previous versions of deep learning, things like RNNs and LSTMs and even CNNs and things like that, starting to replace them with these large-scale transformer-based models. So here are some examples in Bing of how we're using them for things like answering questions or auto-completing searches or suggesting more questions to people. And then we went and took the same model and then we applied it in Word. So let's see how it works in Word.
Bing has been using Turing for the past year to empower its search and question answering capabilities. Let's now look at how we have innovated the find feature in Word in the same way. Let's search for paragraphs related to the terms lead and water. Word finds 5 matches in the document. If I click on any of them, it'll send me to the relevant paragraph in the document. Even if I make a typo, Word will find the relevant matches. This is very useful for complicated words. For example, cryptosporidium, something like that. Okay, so that's the one that I was trying to find. Now, Word can even answer questions about the document. For example, how often is water tested? And the answer is here, between 10 and 100 times per day. You can find information in the document. What about how to reduce lead in water? And the answer is here, to flush it through the tap until it's significantly colder before using it.
So that was the same notion of semantic search and question answering, but in the context of Word and documents. Here we have on the left side SharePoint and using our language models for extracting summaries out of documents. So in SharePoint, when you move your mouse over a document, you can see the summary. So you can get some insight into what the summaries of the document is about. On the right side, we have Teams, and we have a feature called Viva or Viva Topics. And what we are doing is extracting knowledge inside of the large amounts of data that is living inside of the organization. So in this case, this is for detecting projects. So if you see the acronym SOAR, S-O-A-R, somewhere in a Teams chat, for example, we automatically generate this project card where give you information about what this acronym is, and this acronym corresponds to a project, and there are some alternate names for the project. We give you a summary of what the project is about from multiple documents that describe the project, the people that works in the project, and some suggested resources where you can find more information about it. In the case of Outlook, we help you better prepare for meetings. So before a meeting, you can see some insights of the meeting, like some documents that you may want to read, some relevant emails that you may want to read before the meeting so that you're prepared for it, or for suggesting your replies in the case of both Outlook and Teams. So as you get an email or you get a message in Teams, we suggest you some replies so that hopefully that saves you some keystrokes, particularly if you're in a mobile device on the go. In the case of Dynamics, we use it, for example, for virtual agents, where the answers elicited by the agent are generated based on the language model. And then for customer support, where humans want to keep track of how the communication between the customer and the agent is going, we give you information like, in the case of number one, relevant acknowledged articles that you can read for more information about the particular case at hand, or similar cases that you may want to read, or the sentiment of how the conversation between the human and the bot is going, so that you can decide to jump at any point in time. We have expanded now from language into things like language and code. So in this case, we have Power Apps. This is the environment where citizen developers, often that don't have a traditional software engineering background, can go and generate applications in a low-code manner, and we're trying to move that from low-code into no-code, where in this case the user can say, in this interface, I want to show customers from the US where the subscription is expired, and we can translate that into the relevant SQL-like statement. Or in this case, the user showing the development environment an example of how he wants to show information for this particular list. Like I don't want to show the email, I just want to show the first part of the email. So how do we generate the right piece of code to do that? And then we have expanded that into general purpose programming, and we introduced GitHub Copilot some months ago. And this is your AI pair programmer. And what GitHub Copilot does is it's able to generate full pieces of code, like full functions, for example. And Copilot is based on a model called Codex, and this model has been trained on billions of code lines, and it speaks dozens of computer languages and is familiar with thousands of frameworks and public APIs. So an example here, a user just types in the comment, I want to determine whether the sentiment of text is positive, and I want to use a web service. And then Copilot generates the whole function for that. In this case, it's a TypeScript function, and is calling a well-known API in a web service for that. In this case, and the user defines in English the requirement for the function, and it is, I want to parse a list of expenses and return these as triples, date, value, currency, and ignore the lines that start with this particular hash code, and parse the date using a datetime. And here are some examples of the expenses strings, and Based on that, Copilot generates the whole piece of code, in this case in Python, so that you don't have to spend time dealing with sometimes repetitive code, and instead of going online and trying to find how do you go and do these things and copy and paste and then adapt it, simply inside of the development environment, Copilot can generate these things for you. So interesting to think how will software development change as these development environments better translate between the human language, our language, and the programming language, or the language of computers. And we're moving even beyond from language and code into other types of dimensions that we combine, things like images and video and things like three-dimensional spaces and other things. So here you can see an example of a model that we call Turing-Bletchley, where we are asking the model to find things like Tokyo Tower at night, multi-color Tokyo Tower at night, and the model understands how to search for these things. It translates between the language understanding and the pictorial content, and it understands not only English but other languages as well. Anyway, you can find a bunch of interesting images just looking at the pictorial content. And it's interesting to see how the model is able to abstract this understanding of language and images. In this case, we're giving the model a particular image, like this image, Tom Brady, and we say, we want this image but for Patriots, and it does that. And now we want it for Packers, and it does that. The model understands how to combine language with image understanding. Anyway, there's a bunch of interesting ones like this one. I'm running a little bit out of time, so I'm going to start to move a bit quicker. But in this case, we show the Space Needle in Seattle, and we say we want this plus Paris, and then we want this plus Paris, but remove the sketches, etc. Here we have another model called Alexander Multimodal, specifically called Florence. And what this model is able to do is search for particular objects inside of an image. Like in the case of the top example, we asked for The Last Girl, and it finds the book called The Last Girl. In the second one, you have a bunch of covers of Xbox games, and we ask for the yellow one with two funny faces, and it finds it here. And then the final one, we have a photo of people inside of an environment, and we ask for the police with the beard, and it's able to find the police with the beard. And then we have DALL-E from OpenAI, and DALL-E is able to create images from text, like a female mannequin dressed in a black leather jacket and a gold-plated skirt. So these are wholly new images that are not found in the web, but generated for the first time by DALL-E, or a living room with two white armchairs and a painting of the Colosseum mounted above a modern fireplace. And you can see whole new designs of places. And then DALL-E V2, the second version of DALL-E came out last week, and now it's able to do high resolution generation and even broader and richer understanding of the nuance of language and the generation of images. So in this case, we're using all of that computational power to generate a raccoon astronaut with the cosmos reflecting on the glass of his helmet, dreaming of the stars. So interesting to think, how will graphic design change as design tools better translate human language to creation? So I'm running a little bit of time, so I'm just gonna show you quickly. This is how we think of the stack that is allowing us to do all of these things. We have infrastructure at the bottom, large amounts of compute, enabling us to do this, machine learning acceleration software, some libraries that we're using, some compilers and runtimes that we're using. We have a machine learning service that allows to manage all of this infrastructure to do the data science work of training the jobs, deploying them, optimizing their inferencing, etc. We have all of these AI models like Turing and Florence and GPT-3 and Codex. And then we have API services that are allowing us to use these models. And all of these API services, we're making them available as part of the Azure Web. So you can go and find them in Cognitive Services or Cognitive Search or the new Azure OpenAI service. So the same things that we're using in our products, you can go and use. So I'm gonna skip this quickly, just talking about this, the services that you can go and find. The infrastructure, as we said, large amounts of compute. You can use as little as much as you want, from 8 GPUs to 6,000 interconnected GPUs. And we're really in the fifth industrial revolution. So we have gone from the steam engine to electricity to transistor to robotics, and now we are in AI. And let me just finish by saying, what a great time to be alive. If you want to learn more about all of this, here are some places where you can go and find more for AI at scale or Azure Cognitive Services or APIs there, or in OpenAI, Azure Search, as well as Azure Infrastructure. So with that said, thank you very much for joining the talk.